So Ken, thank you so much for joining us tonight. We're going to start off with the most exciting part of the show. So welcome back to All Space Considered. I know you've spoke at Griffith Observatory a few times. You were here for the Hubble 25th anniversary. That's a crazy number, but we had a big party essentially up at Griffith Observatory for 3 or 4 days. I think it was 4, and you joined us and talked Hubble. And I know you've dropped by All Space a couple of more times, once or twice. So welcome back, and it's a thrill to have you here tonight to tell us about what's been going on with JWST.
Oh, thank you, David, for the warm welcome. It's great to be back, if in a virtual sense, tonight. And welcome to everybody who's joining us here tonight. I'm going to talk to you. Well, first of all, I'm the operations project scientist on the Hubble Space Telescope and the ground system scientist on the Roman Space Telescope. I don't work directly on Webb, but of course I'm surrounded by folks that do, and I've been talking to them and hopefully have the inside scoop for you as we go through here. So let's move on. I do want to start by pointing out, which probably something a lot of you already realize, is that JWST is not really a replacement for Hubble, but rather a successor to it. And that's because Webb will primarily look at the universe in the infrared, the red part of the visible spectrum, and the infrared, redder than the eye sees and redder than in most cases gets through the Earth's atmosphere, while Hubble actually looks at the blue part, the visible in the blue, and out into the ultraviolet, which is bluer than the eye sees. So they're looking at different parts of the spectrum, different colors, and therefore they're going to get different information on the objects they're looking at. Webb's larger light collecting area, coupled with the improved infrared sensitivity, or the infrared coverage that it has, will allow it to peer back further into time than HST, and is actually one of its prime driving goals, to get back to try to see the first galaxies, the first stars, when they first turn on after what's called the Dark Ages, which started a couple hundred million years after the Big Bang. JWST sees cooler material and peers through and into the interior of dust clouds, because the infrared light with its longer wavelengths can actually wiggle around dust particles more easily and allow us to do that. HST sees hotter material and can see the exterior details of these same clouds. So that's just some of the differences that one can see using observing at the different colors that the two telescopes look at, but there's a lot more. So they're very complementary to each other, and together they will extend the science that we can do tremendously. Hubble has been, we have been waiting for Webb to launch for quite some time now. As our own telescope aged, we wanted to be able to use the two telescopes together, and we were very happy to see it launch last December and to get into this mode where we can work side by side. I'll just do a few introductory comments on JWST to put it in context. It's a very large telescope, especially the sun shield. Let's see if I can get the laser pointer to work here. Yeah, see here, this white extended area here is a sun shield about the size of a tennis court. It's actually a 5-layer mylar foil material, and that's designed to keep the upper part of the telescope cool. We'll talk more about that in a second. It's also located at a different spot in orbit than Hubble is. Hubble is in low Earth orbit, only 340 miles up. That was in part so the space shuttle could get there and service it, as it did 5 times over the early years of Hubble. That's, of course, no longer happening because the shuttle is no longer flying, but that's one reason it was down in low Earth orbit. JWST, on the other hand, is going to be out at what's called the Lagrange 2 point, L2, which you see here. And that point is located on a line from the sun, draw it through the Earth, and go another 1,000,000 miles out. And that is the L2 point. Webb is orbiting slowly around that L2 point, as a lot of other telescopes are doing and will do in the future. That gets it further away from the heat contamination of the Earth and the Moon that objects, that observatories in low Earth orbit will run into. More visualization here of the distance. Here you see Sun, Mercury, Venus, Earth, only 93 million miles there. And then if you look at JWST out here at one end, about 1,000,000 miles further out from the Earth. as an illustration of the wavelength coverage, the difference in wavelength coverage, the different colors it looks at, you see here on the left, the blue box shows the wavelengths ultraviolet and visible, mostly, that Hubble covers. Webb has a tiny overlap in the red part of the visible spectrum, and then goes off further into the infrared substantially than HST. And as you see on this same chart, other observatories are listed. WMAP goes off into the microwave, the VLA and the radio, RXTE and SWIFT down in X-ray and gamma rays. So we have a whole fleet of telescopes up there. These are two of the biggest, HST and JWST, but they are working together with this larger fleet as well. To set the stage for what we're trying to do with JWST, one of the deeper, what we see here is look back time going back toward the Big Bang on the right part of the screen here. The HST Goods and Chandra Deep Field combined, where we took data from both telescopes and combined it, got back to something like 1 billion years here after the Big Bang. We've gone a little bit deeper, further back in time with very specialized observations using gravitational lenses, for instance, in the sky. But for the most part, that defines the edge of what HST can see. JWST is designed to go further back to within something like 200 to 300 million years after the Big Bang. And we hope in that difference between where Hubble looked and where JWST is going to be able to look, we will see both the first galaxies and earlier than that, the first stars to light up after the dark ages. So that's the holy grail that Webb is looking for. Hopefully we'll find those events, the first stars and the first galaxies, easily within the capabilities of JWST, and we'll see a spot where there aren't stars beyond that JWST would see if they were there. That will inform our theories of the origin and evolution of the universe, and is a very important item. JWST will do a lot of other science that we'll talk about, but that's kind of the holy grail. Let's find the first galaxies that turned on, the first stars that turned on. Looking at the structure of the telescope, a little bit more here on the left side, you see we're looking down on the top of the telescope where the optics are. The science instruments are behind the mirrors here, behind the 18 segments. The secondary mirror is up to the right here. So light comes in from the target off on the right side, hits the primary mirror, the 18 mirror segments, goes to the secondary mirror up here, and then down through a hole in the center of the primary mirror to the science instruments. If you flip the telescope over, you see here the sun-facing side. This is where all the components that don't need to be cool and can be in full sun are there. The solar arrays are obviously there. You've got steering and control jets down here, antenna, communications to the Earth, and star trackers. But the whole point of this star shade is to keep the science instruments and the optics cool, because if we don't keep them cool, they give out a lot of infrared radiation, which we would feel as heat, and that would confuse and add noisy background to our observations. Now, I wanted to mention this as I called the talk Commissioning JWST, and that's mostly in orbit, but there's a lot of testing that goes on the ground before we get there. So I just wanted to show you a few pictures from that. These are two pictures showing the prepping and testing of the mirrors at NASA's Goddard Space Flight Center, where I work. You can see on the left here, one of the final mirrors with the gold coating, and a test mirror that's aluminized like our normal mirrors are. We used gold on the Webb mirrors because that allows us, that reflects infrared light at a much higher efficiency, and we're trying to maximize the efficiency in the infrared. On the right, we see an experiment that was done to see if there was a way to safely clean the mirror if it were to get contaminated during integration and test on the ground. So this is a test mirror here, not one of the final ones. You can see it doesn't have the hexagonal shape that the final mirrors do. And what you see here is a technician using a carbon dioxide snow to blow off particulates, to blow off molecules that might be contaminating it. And it was designed to only be used if something got contaminated during the ground INT testing. Moving along to October of 2016, It's the first time that we at Goddard got to see the entire mirror array put together. It's behind this glass wall, which is on the side of one of the largest clean rooms, at least in the eastern part of the US. This is a class 10,000 clean room, very high quality air. There's filters along the right wall that you don't see in this picture that filter all of the air coming in, and the air flows across in a laminar, flat fashion, very little disturbance, no turbulence or anything, keeps the air in there very clean. They put this, both the mirrors and the instruments together in this room, and they have this little mezzanine area where you can go in and look at it. And it was all, of course, very exciting to walk in there and see this massive mirror standing up above you, and made you feel that we were finally getting close to launch. This next one is a kind of a cute picture. It shows the mirror head on and a very large group of people trying to get a look at the mirror before it's shipped off to Johnson for further testing. So you see here, this rectangular shape that you see is actually the window reflected back, the other side of the window reflected back toward us, and you see all the people standing in there looking out. I must be in there somewhere since I took this picture, but in this particular one, I haven't found it. I have one where it's much more clear. Ground testing at Goddard continued with testing of the science instrument module. So we assembled the mirror array there, tested that, and then we put the science instrument module together with the various instruments in it. This is on the left, is it in the clean room, and then it was transported and put down into this massive, what's called thermal vacuum tank. Drop this down gently into there, put a domed structure over it, and then you can pump all the air out, get to a vacuum like that in space, and then you can also lower the temperature or put the temperature through cycles like you would see in space. And you do this to make sure that everything's going to hang together, that everything functions in a vacuum, and that no wiring or other components pull apart when you actually go through the temperatures you expect to see in space. Then the mirror and science instrument were shipped out to the Johnson Space Center in Houston, put together with the rest of the facility, and put into this even larger thermal vacuum tank, which is actually from the Apollo era. It was what was used for what was called human thermal vac. So the astronauts would go into this chamber, and there would be a simulated lunar surface in there. They could go in, try using their tools, try moving around and making sure that they could practice their stuff in something that simulated the lunar environment. That chamber was completely refurbished for Webb and used to test the whole thing coming together. You see on the upper right here, it exiting the chamber. Then it was moved on to Grumman in California, and you see it in the clean room out there as they were testing the deployment and tensioning of the sunshade. And then I also tested out there, putting it together to fit into the Ariane rocket fairing and making sure it would unfold from there okay. So they packaged it up there and then sent it down to Kourou in French Guiana for the launch that we all saw on Christmas Day in 2021. Just a beautiful sight after many years of delay and many technical challenges. Went off without a hitch. Was wonderful to see, just count straight down, no stops at T-20 or T-5 or T-20 seconds, as we had gotten used to with the shuttle program. Went off beautifully, and this picture here was the last picture that we saw of JWST heading off toward the L2 point. And just to remind you, this is the approach attain, came out of Earth here in a lazy loop out to go into a very wide orbit around the L2 point. So you don't sit at the L2 point, you actually orbit around it. That keeps it in the sunlight. Most of the time, if you're exactly at the L2 point, you'd be in the Earth's shade, but it also is easier to control that way, and it minimizes the chance of collisions with other observatories that might be out there. This shows JWST's unfolding sequence, which I don't need to go through because I think you saw that very nicely in the opening video, but various stages that took a couple of weeks to actually get to the fully extended and final version that looks like an operating telescope. So at that point, once everything had been unfolded and deployed, we got into the commissioning phase. And I'm not going to, don't worry that you can't read this. This is very small print. I'm going to blow it up in the next slide. I'll take the left half and put it on the top and the bottom half on the bottom so you can see it, but I just wanted to show you the complexity of it and how long it takes. So here, starting at launch plus weeks is what's labeled here. From 0 to 4 is spacecraft deployment, mirror alignment and cool down, goes through week 8 out to week 12. All along, you're starting to deploy the mirror segments and identify which segment is producing which spot of light, and then start phasing them up so they all produce light at the same part of the detector and give you a single image. So various stages of that fine phasing here, final phasing, as you get out toward week 16 or so. And at week 16 is where the instrument commissioning takes place. So up through here, you've just done the alignment of the optics, but you haven't actually checked out the science instruments in any details yet. So you do, starting at week 16, the instrument commissioning and the instrument node checkouts, starting about week 19 or so. And that goes all the way out to week 28. And then the first images were taken shortly after that. So how many science instruments are there on Webb? And you see here the 4 called out, one called NIRSPEC, Near Infrared Spectrometer, Near Infrared Spectrograph, the NIR ISS, the Near Infrared Imager and Slitless Spectrogram, NIRCam, the infrared camera, and MIRI mid-infrared instrument. So you've got one spectrograph in NIRSPEC, one combined imager and spectrograph with NIRIS, NIRCam as a camera, and then MIRI in the mid-infrared. The only one that works in the mid-infrared actually has both camera and spectrographs in it. To set the scale of this image, this is the background picture is a section of the Virgo cluster of galaxies. The image is about 2/3 the size of the moon as you see it from Earth. And then over that, we've placed the Webb field of view. And notice here that the 4 instruments look at different parts of the field of view of the telescope. So if you want to observe, say, this bright galaxy here, you have to move the telescope so it lands in the MIRI aperture or the NIRS aperture or one of the NIRCam apertures or NIRSPEC. So you don't have detectors in all areas of the focal plane. You have to sample it depending on what instrument that you do want to use. Another slide that I'm not going to read everything on, just want to point out how many different instrument modes there are. So each instrument has multiple modes of operation. And if you go and read on the right side here, you can see all the different ones: imaging, coronagraphy, spectroscopy, time series, etc. During commission, each mode has to be tested, calibrated, and verified, and only then is it decreed to be ready for use by the astronomical community. We do carry out the process in parallel for all 4 instruments over L+16 to L+28 weeks. And this next chart just shows that in a different graphical form. At the time that this chart was put together, everything had been done except for the coronagraphy mode in NIRCam. But again, this is why we had to wait so long to actually see the first science images. You had to go through all of these calibrations and tests to make sure everything was lined up and ready for use. So with bated breath, we got, originally the plan was to actually wait until July to see the first images at all. But some of the early test images were so good that it was decided to show them and let everyone share in the excitement. So this is one of the early telescope alignment images. This is the end of all the optical alignment, and you see it's absolutely gorgeous. These spikes here, the 6 spikes are expected. They're caused by the hexagonal shape of the mirrors as light diffracts off the edge of the segments. But you see a lot of in focus distant galaxies in the background as well. This kind of image sharpness check had to be done for each of the instruments. And you see here the 4 science instruments that I mentioned earlier, everything looking in great shape, and also some images from the fine guidance sensor, which is strictly speaking not a science instrument, or not normally used as a science instrument, but used for guiding the telescope. But as you can see, it actually gets some pretty dramatic pictures all by itself. And this is a gorgeous page that shows how beautifully focused everything is of all parts of the focal plane of the telescope, because as I pointed out, these different instruments sample different parts of the focal plane. So everything is not only aligned at the center, but in all directions around that. And it's just a gorgeous image. Next, I'm going to zoom in on the MIRI data a little bit, just because there's a nice comparison here. This is a sort of apples to apples comparison that shows data from MIRI on the bottom, and on top something from the Spitzer Space Telescope, which was the previous infrared telescope. And you see the dramatic increase in quality and resolution that you see here in the MIRI data, which is taken at 7.7 microns, 77,000 angstroms, versus the Spitzer Space Telescope infrared array camera at 8 microns. Almost exactly the same wavelength. Spitzer one's a little bit redder, but you can see the dramatic improvement here and how we can see the gas in this area in much, much finer detail. And then we have one more test image here that I just had to show you. This is from the fine guidance sensor thermal testing. And again, this is not normally thought of as a science instrument, but it was a rich data set. It had 72 exposures over 32 hours because they were testing how stable the imaging was as the temperature changed. And that's important to know to optimize your future observations. Because it was taken, there were so many exposures over such an extended period, it turned out to be among the deepest images of the universe ever taken, which is pretty good for a star tracker. Of course, that record lasted for about a week until the first light images came out from the science instruments. But at least for a moment, the FGS had its moment of glory. Okay, now to the part that probably everybody was looking forward to, the first light JWST images. And the first one here in no particular order. This one is shows SMACS 0723. This is a massive cluster of galaxies. And we were observing this for 2 different purposes. One is to actually look at the cluster members themselves, which are the bigger and brighter galaxies that you see all around, as well as some fainter background galaxies. And also, we're looking at these arcs in the image. They're a little faint, maybe a little hard to see on here, but here's some of the best ones. Those are images of very, very distant galaxies behind this massive cluster. And this is the gravitational lens that I was talking about earlier. There is so much mass in this cluster in front of us that it can actually bend the light and amplify it that's coming from behind the cluster much further out. The main galaxy cluster here is about 4.6 billion years light travel time away. We are actually seeing distant galaxies through this gravitational lensing process at greater than 13 billion light years in the past. So it's a very powerful image, and this, of course, was even deeper than the FGS image that we showed you there. There was also, this is mostly what you saw in the newscast, but there were a spectrum taken off on a tiny light to the side. Well, if you look in the side image here, this is a slice in this area here at the 9 o'clock position. If you go in here, there's a little tiny red dot. We actually got a spectrum of that smudge of light, and not only detected the galaxy, but saw some very clear emission lines here of specific elements like hydrogen and oxygen. People got really excited about this pair of lines out here due to the oxygen. I don't think anyone really expected to be able to see that. So we not only got a very, very deep image of the universe here, we're actually starting to get some very detailed physical information through these spectra. And if we're able to do it on that tiny dot of red light that you can't really even see in this big image here, imagine the richness of this that we're going to have when we're able to look at all of the thousands and thousands of galaxies in this image. We also took a look at a exoplanet, seeing what JWST could do there. The system is called WASP 96b. And here, this is a transmission spectrum. So the higher the plot goes here, the higher the data points, the more light that's being blocked by something in the planet's atmosphere. Basically here, we're looking at the light that gets through the planet's atmosphere along the edges of the disk. We have the sun, the star behind the planet. Light comes through, is mostly blocked by the planet, but some sneaks through the atmosphere, and you can look at how that's different than the light that's coming from the star directly. And very excitedly, these four peaks, one there, and there, and there, are all signatures of water vapor. So we now have, in the first exoplanet observation with JWST, signatures of water vapor, which is one of the possible signs of life. Now, of course, just seeing water vapor by itself doesn't tell us there's life there. We need to find other chemical elements and signatures to be sure of that. But finding water around this planet is, means we can detect water given the right circumstances, and gives us hope for really finding, being able to do what we want, characterizing the atmospheres of exoplanets. We also got what's called a transit light curve, and here you're just looking as the planet passes between the star and ourselves. We're looking at the decrease in light coming from the star that's simply blocked by the planet. And you see that here, starlight on the left. That's when the planet's off to the side. It starts dipping, and this is when the planet is directly in front of the star, and then it starts coming out of the eclipse and coming out the other side. What's spectacular about this, if you had looked at this kind of observation 10 or 20 years ago, you would see the noise in the signal would be almost as large as the total signal. And here it is so ultra clean that you can use this to determine things very more precisely, like the planet's orbit, its radius, and the like. And this data is just incredible when you look at it. We'll be able to do this on a whole slew of exoplanets with Webb. Moving on to the Southern Ring Nebula in two different colors, near-infrared light at the left and mid-infrared light at the right. And you see even within JWST, there's dramatic differences in the structure. And if you compare this to a Hubble image in the ultraviolet, it would yet look completely different again. So having the different colors of light to look at lets you see different layers of the object at different temperatures. These are going to be showing material here that's cooler than what HST at a similar image. And you use them all together, you'll get much more information on the nebula. We're moving further out here, out of our own galaxy into very distant galaxies, not quite as far as in the deep field image that you saw earlier, but this is a very famous formation of galaxy called Stephan's Quintet. 5 galaxies that are interacting with each other strongly, so all of their structures are rather radically disrupted. You do see on the left here signs, these arcs of star formation that are happening as the galaxies interact and push material together and enable stronger star formation. This on the left is a image combining observations from both NIRCam and MIRI, so you're getting a broad range of wavelengths and more of a full color image. On the right is something taken just with the NIRCam, I believe, that shows some things in finer detail. You see shock fronts in several spots here, these curved arcs, brilliant bits of star formation, etc. And then an image that you saw earlier from the Carina Nebula. And what you're actually seeing here, this nebula is part of a very massive nebula that covers a large section of the sky. The star field here is actually a hole in that nebula. So you're looking at the inner edge or the outer edge of this hole that's full of stars, but it has been cleared out over the eons by radiation from the stars have formed within. The nebula itself is a hotbed of star formation. You see a stream of faint material coming off the cloud and moving upward in the picture. You see pinnacles of dust here where there's been a really high concentration of dust and gas that erosion from the starlight has not been able to pull off. All sorts of structures and details. This kind of image that you could spend years looking at. If you look right about here, there's a really odd arch shape, sort of like a tilted arch that's falling over, almost like an elephant trunk. And you look at stuff like that and you start thinking, I really don't know how to make something like that. So it's the kind of thing that intrigues you and it challenges the theoreticians. You see some areas here where material has been cleared out by the hot stars inside, and in general, very turbulent environment with all sorts of things going on. This image is looking at the same area, but again, using images from both MIRI and NIRCam, so looking at both the mid and the near IR. Again, you see the streams coming off as material evaporates. You see a lot more stars in this image, a lot more vacant areas as you use the wider variety of light, different colors of light to probe it. And I think that's it for the new images. We'll, as David mentioned earlier, be showing some near the end of the show that have come in more recently, but we wanted to leave that for the end time. I did want to remind folks, if it will advance, there we go. Where do we go from here? And JWST's driving goals cover a variety of topics, looking back, especially like you saw in the deep field at the early universe, trying to find the first stars and galaxies, and then trying to study how they evolve over time. And this is where working together, one topical area where working together with Hubble will work very nicely. JWST can observe the very earliest galaxies, and Hubble can take over as we come closer to our own time and get a complete picture of how galaxies evolve with time. JWST would be looking at the stellar life cycle. These clouds here, like you saw in Carina, typically have both stars that are being born and stars that are dying within the same environment, and provide an excellent opportunity for understanding how stars are born, evolve, and eventually die. And of course, the search for other worlds is really the end goal of most of what we do, trying to find other worlds, especially trying to find habitable other worlds, and in the very, very end, signs of intelligence. We may not get there with Hubble or Webb, but we are paving the way to finding and characterizing the planets as the next step in that search for life elsewhere. And I'll say, for more information, home pages on the web for all the big NASA missions are at nasa.gov/Hubble/Webb or /Roman. The Roman Space Telescope comes after Webb. We've used this common nomenclature now so that you can easily find it. You can follow all our missions on Facebook, Twitter, and Instagram at NASA Hubble, at Webb Telescope, or at NASA Webb, and at NASA Roman. And you'll get continuous updates about what we're looking at, and some of the most recent observations are there, as well as on the websites. You're welcome to follow me on my personal Twitter account at KenAstro, but be warned, if you do that, you'll get a lot of Star Trek, Disney, and Renaissance Festival info and photos, as well as NASA and Hubble. And I think I'll end there and hand it back over to David.
Awesome. Well, thank you, Ken, for that. That was a fascinating look at the testing of the James Webb Space Telescope, to say the proper name, of course, at least once here, and the launch, and then, of course, these first science images. That it's truly a new age that we're in. We've crossed over into new territory, just like when the Hubble Space Telescope had its corrective lenses put on, of course. Once they got the primary mirror fixed, it opened up a whole new era for astronomy, and we're seeing that happen again, which is incredibly exciting. So folks, I've seen questions come through our chat. We'll get to your questions in just a minute, but if you asked a question early on, you might want to type it back into the YouTube chat again, since it may have slipped by. But I'm going to open up our questions with, I've noticed that there's sort of a it looks like there's a stellar stream in that cluster image to me. I worked on the Andromeda Galaxy, and as small galaxies fall in, they leave behind a trail. And it looks to me like there might be that in that cluster image. You can see it there. Let me see if the pointer's still on. There it is. It's this stuff that kind of goes around like that. Yeah, exactly. Is that actually what we're seeing there? Do folks know if that could be stars that are in the cluster between the galaxies?
Yeah, that's exactly right. We do think that's intracluster light that's produced. It's basically stars that have been stripped out of the galaxies as they've collided with each other, and kind of strewn in the core of the galaxy, and actually out quite a ways when you look at it. So it's a very cool way to be able to probe the gravitational potential of this massive galaxy cluster, and a way to see where the dark matter is, because we can see how this fog of stars moves, how it's changed by interactions with the overall gravitational potential, but it's going to move in ways that probably can't be explained by the visible stars, and that'll give us a clue as to where the dark matter is and how much of it is in different spots.
Wow, fascinating stuff. Chris, do you have a question?
Yeah, actually, I do. I'm fascinated by the fact that the JWST is floating without a tube. The optics are completely exposed to space. It seems like a dangerous thing to do. And I'd heard a rumor that the telescope, one of the mirrors, actually did get dinged by something. Is this serious? Is it a concern?
Well, it's not completely unexpected. This has even happened. Hubble has been hit by various pieces of small micrometeorites over the years. We actually have a hole in the high gain antenna, one of the high gain antennas, but it doesn't hurt very much in that case, because we still have, the antenna is mostly intact, and we have plenty of signal to get back to the Earth. In the Webb case, the hole is in one of 18 of the 18 mirror segments that are there. I did actually check with my counterpart on the Webb telescope, asking, what they think the impact is. And they say, at the moment, the change in throughput, how much light is gathered by the mirror and sent to the science instruments, has not been measurable. So it's not impacting the amount of light gathered by the segment, and certainly by the telescope, by very much. It has definitely impacted the what's called the wavefront, basically the focus. It's because the mirror's been distorted a little bit. Now, some of that you can correct for, because these 18 mirror segments are actuated. That's how you get them all into phase and working together. So some of that error you can probably take out with the actuators. It's unclear at the moment how much can be taken out, but it is clear that we are still well within spec. The mirrors were working together and performing to a large degree, much better than the specs that we had on them. So we had plenty of margin for problems like this, and it was intentionally designed to be overperforming, because we knew there's debris out there, and we expected to see events like this. We don't know, until we see another kind of hit, whether we're going to see them at the frequency expected. There are predictions for this. But one case doesn't really tell us what the overall frequency is. So we'll wait and see if it's a bigger problem than we were expecting. But right now, it appears that we've got plenty of margin. The light gathering capability is not hindered much at all, and the focus is still well within our specifications.
It's great news. So Patrick, do you have a question in mind? Oh, but you're muted.
Now, take two, unmuted. I find the atmospheric composition measurements very interesting and very exciting to find water vapor from an exoplanet. Is there also a way to determine the temperature of the water vapor, if they're forming clouds, or is it just water vapor? It's so hot, it's just gaseous.
There might be ways to do that by looking at the ratios of those four peaks. I'm not 100% sure. There is the slide that's up there now actually shows the white dots, which are the measurements, and the blue line is the best fitting model. So you see, we don't actually match it precisely. And it's thought that one of the reasons that the observations are a little higher than the peaks in the model is because there are clouds, as you mentioned over there, causing more light to be blocked than just by the oxygen atoms themselves.
Interesting.
And of course, those models, the blue line there, contain all of the parameters that you're talking about, temperatures and densities, and as well as abundances, the amount of water. So if we can find a model that actually matches the observations better, that's probably the best way to kind of figure out the temperatures and densities, is by fitting all of the data with a single model and not just using maybe simple line ratios like I first said.
Thank you.
Well, awesome. So I am going to turn to our YouTube audience here. And I know I saw a question, is the MIRI instrument, which is the longer wavelength infrared camera, is it expected to last as long as the telescope itself, or will it sort of run out of coolant like what happened on Spitzer, where the long wavelength instruments had to be shut down?
That's a good question. I think the cooler, and I don't want to be quoted on this, I think the cooler doesn't use an expendable like that, that it's basically a electric kind of cooler. It's active, it's not just radiating into space, but I don't think it's quite as fragile as the ones that had a coolant in it, like the NICMOS did on HST, for instance.
Yeah,
if
that was
different, Dave. Please do say.
No, that was my understanding as well. That was one of the reasons for having these big sunshades, was to get things a lot cooler, and then using other means, other space refrigeration, shall we call it, we're able to get down to the lower temperatures. So I don't believe there's any coolant to run out on. There was another question that they wanted to know, was the cluster image, was that chosen because nothing was there, or did they pick that image because we knew that cluster was going to be there?
Yeah, we certainly knew the cluster was going to be there, the SMACS 0723, and we have other observations of it, but just not as deep. So yeah, it was picked because the cluster was there, and we knew it had enough mass to do the gravitational lensing, because of course we wanted to see what JWST could do when it was given that extra tool. Both HST and JWST can actually see further back in time, further out into space, using the gravitational lensing technique by observing clusters that have a lot of mass and can amplify the light force than they would without that. Side by side, looking without in a direction that doesn't have a big cluster like this, JWST will go further and deeper because it's got a larger mirror. But they both can go better than you would think, from basic telescope information when they do look in the direction of a massive cluster.
Yeah, the big cluster acts as a gravitational lens, and it allows us to see further away, and it magnifies the brightness of these galaxies as well. A lot of these arcs you're seeing are the same galaxy, so there are multiple images of the same galaxies that are back there, and stunningly, some of the images we get are kind of normal-ish looking. I don't want to point any out directly because I don't have the map in front of me, but folks have already started to map which of these galaxies is the number one galaxy, say, and there's multiple images of galaxy 1, and then galaxy 2, there might be 4 or 5 or 6 images of it. And some of them look remarkably like a little spiral hanging out there, and they're not, yes. These are not, some of them are not as disturbed as you might think they are, but there's going to be some fascinating papers coming up very, very soon.
And the real fun begins is when you try to model the mass distribution in the galaxy cluster, because if you do that, you can actually reconstruct the images of these from these distorted images. Yeah, but that's a really difficult thing.
There is a mass model for this, believe it or not. I don't believe it's been published, but I was tweeting when this was first released, that very first night. I was tweeting back and forth with some of the folks that are on that team, one of the postdocs that was on that team that had helped develop a model, and she said, here's the model we have for it, and it'll just get better now that they have this amazing JWST image, they're going to be able to tinker and improve the model, and then, like you said, they can reconstruct what these look like. It's just super, super thrilling stuff. So I'm just going to ask one more question. I think it was one of our first questions that was out there. So sorry, folks, that we didn't have. Well, I'll ask two. So the two questions were, how much of the science from Hubble will be verified by JWST? And the next question that I'll ask, the final ones are, can JWST observe complex modules like would exist on Earth? In other words, like human-made chemicals. Could we use it to go find intelligent life, let's say, that might be polluting an exoplanet? Would that be something we'd be able to see with Webb?
You know, I'm not aware of any particular chemical compound that falls in that category. I mean, who knows until you start looking at these detailed spectra, something might pop up. But you'll notice that when you look at the exoplanet spectrum that we had here, we're seeing some pretty broad features due to the water vapor, and presumably that's a very abundant molecule in this atmosphere. So you're probably, I would guess, going to have a hard time seeing trace constituents of anything. You're at this ability here where you're probably looking for things that are major parts of the atmospheres here. So I mean, especially if you had a really bad industrial contamination, maybe you could see it. But I would think in most cases, we're looking for the molecules that are primary constituents of the atmosphere, not trace stuff. I think it's probably another observatory or two further in the future.
Unfortunately, folks, including Amber Strawn, Dr. Strawn, has said that Webb is not designed necessarily to prove life is on one of these exoplanets. It can see some of the constituents, and who knows what clever tricks people might use in the future, but we really need a big optical space telescope that can do spectroscopy in conjunction with JWST. Hubble's just a little too small to be able to do it, and you need the resolution. But if we had, say, a 10-meter or a 15-meter class optical telescope up in space, along with Webb, we could leverage the two together and get a much clearer picture if there was life. So the final question that was from our YouTube chat, again, are there any Hubble discoveries, quote unquote, that you think we can really nail down and verify with JWST? Do you have any in mind? I know that the answer to that is of course they'll be able to, but are there any that you're looking forward to that we're sort of maybe this is happening, but now that we have JWST, we can really figure it out?
Well, I think the obvious thing is in trying to understand the very oldest galaxies, the very earliest stars that Webb is going to have the sensitivity to really look at. We've recently, Hubble has been able to image the most distant individual star ever seen, and we probably have, or at least had, the record for the most distant galaxy of 100 billion or 200 billion stars. But when we're looking at those, they're tiny smudges of light with not a lot of ability to see the structure in them, with not a lot of ability to get a good spectrum to really see the chemical constituents and understand the physical parameters, temperature, pressure, density, and the like. Webb, with its larger mirror and with its infrared sensitivity, ought to be able to see these very distant objects, be they stars or galaxies, much better with a lot more light coming into the instruments, so that you can spread it out a little bit more, get a better look at the details of the spectrum and what kind of elements and molecules are in it and what the physical conditions are, just because you have the light and the resolution that you don't quite get in the infrared with HST. So that's the area where I'd look for the biggest improvements. But I'm sure every time we launch a new telescope like this with substantially increased capabilities, we get a large chunk of the results coming out are in the unexpected category. I think with Hubble now, we're probably at a level that maybe half of the science that comes out of it is stuff that was not expected before it was launched. Just, completely, not superfluous, but just completely out of the blue, as it were. And I'm sure the same thing is going to happen with JWST. That's the fun of it. You do the stuff you expect to do, and you do it really well, and then a whole bunch of new information comes out, and some of it will puzzle us, like the discovery that the expansion of the universe is accelerating instead of slowing down with time, which was partly Hubble and partly observed by many other telescopes around the ground.
Well, thank you so much for joining us, Ken. Just a fantastic look at the JWST, the new telescope. I can't wait to have you back in person to talk about the next round of science images. We'll have to have you back. And then, of course, when the Roman telescope gets launched, we'll have you back to talk about that, because that's just, I'm super excited about a telescope that'll be able to get M31 at just a handful of pointings. So it'll be great fun.